All right. So today I bring you the rubber stopper lab, a lab we would have done in school, but I think we'll be able to do it pretty well this way. What I have here is a rubber stopper like that would go on top of a test tube in your chemistry class, and then some fishing line, and it's threaded through this plastic straw actually that would be used for bubble tea. And then at the bottom of the other end of the fishing line, there's a loop where I can hang a mass from it. This is a 100-gram mass. So I'll hook that on there. And the way this works is that I'm just going to let that mass hang down. And obviously if I just let it hang down, it would accelerate towards the earth. But in order to exert a balanced force on the mass, I'm going to be twirling the rubber stopper in a circle. So it's going to be going around my head like this. And first of all, I want to try to make it go as parallel to the ground as I can. But if I'm twirling that at just the right speed, you'll notice that the mass doesn't accelerate towards the earth. It just remains in its position. So it must have balanced forces acting on it. And then in terms of the rubber stopper, it's moving in uniform circular motion at a constant speed. So it must have that constant inward force acting on it as it's twirling here. So we can use this apparatus to answer a couple of questions. There's a variety of experiments you might do, but for our purposes for the rubber stopper lab, what we're interested in exploring is what's the relationship between the radius of the rubber stopper's rotation, so if it's moving at a relatively short radius, and the speed that it has to be moving in order to have a balanced force acting on the hanging mass. Since I'm not changing the mass at all, really that force should be constant throughout this, the force that needs to be exerted on the rubber stopper to maintain that circular motion at a particular speed. Okay, so let me write that down here. The question that we're really trying to answer is, so what is the relationship between the radius of rotation and the speed that the rubber stopper is moving at that radius? So I'll show you just a quick demonstration about what that would look like. It's too bad that we can't do this in school. So if I'm at a pretty short radius, if I was doing this lab, I'd be measuring what's the distance from the rubber stopper to the center of its rotation, so center of the straw there, and how fast it's going. So I would get it going at enough of a speed. Ooh, too fast, hang on. And actually, the reason that this blue tape is here is for me, as I'm doing this lab, I would slide that up to give myself a visual cue to know that I'm not changing the radius of the rotation because that tape isn't moving up or down relative to where the straw is. Okay, so I get it moving at that speed at this radius and just maintain it. And then it's really nice to have some partners here, because what you would want to do is maybe count how long does it take using a stopwatch for a certain number of revolutions here. So I would count maybe 10 revolutions, start my stopwatch, and measure how much time it takes for those revolutions. So the measurements that you would be taking is what's the length of the string here that's exposed, so what's the radius of rotation, and then how long did it take for 10 revolutions. And then we're going to do that at different radii, so we'd move our tape down so that the radius would be longer in this case. Same type of experiment where we're going to start the stopwatch and let the rubber stopper take 10 revolutions and stop the stopwatch and measure that time, also measuring the length of the new radius, and do that for, let's say, 8 different radii. I will provide you with that data tomorrow so that you can actually analyze it. If you have Excel or Sheets, you'll be able to graph it and look at what the relationship is. today your main job is to finish these like pre-lab questions that I've posted and make your prediction of what that graph will look like. So one thing I want to go through is just what we're actually measuring real quick. So what we're changing, what we're manipulating is the radius. So that is R. And then, so we'll have a column's worth of R's here. And then our responding variable, what we're actually going to measure is the time for 10 revolutions. So I'd have 8 different radii and then 8 different amounts of time for those revolutions. Now we want to get that revolutions into speed here. Okay, just had to make sure my video is still going. So I want to take that time for 10 revolutions and convert it into something like velocity, meters per second. So I'm quickly just going to take you through what that conversion would look like. So basically I know, side note, the time, let's say in seconds, for 10 revolutions. The first thing I would do is actually flip this. So I would I would actually take, for one revolution, how much time does it take? So first thing I would do is flip this and say, I want to know for one revolution, what's the time? So I'm going to put this into 10 rev divided by that measured time. If we have 10 on top and we divide by that time, we're already getting the time for one revolution. But then we really want this to be in terms of meters per second. So in order to know how far it's gone in one revolution, what you would need there is the circumference. So we're going to have 2 times pi times r is the distance in meters. So this is just my units, meters, in one revolution. So then my revolutions will cancel out here and I'll be left with the meters per unit time, which will be our units for velocity. So meters per second, to know what was its speed during that rotation. So at this point, go ahead and complete those part 1 questions. What we're really going to relate this to over the next couple of days after we've gotten the data is how does this relate to the motion of planets when we're looking at the night sky. So there is going to be some model extension taking this rubber stopper rotation and the relationship between distance and speed back into orbital motion. We're going to see how this is similar and how it's different, but this is just our first stepping stone. Getting us back into looking at the orbital motion of all these celestial bodies. So thank you again for watching. I hope you all have a great day, and I'll see you later.